algorithm. Now let's start the derivation of radix-2 FFT algorithm. Since FFT is just an optimized implementation of DFT, so we will start from the DFT analysis equation, which can also be written in the form of Wn notation like this one, because Wn is equal to exponential minus j2 pi over n. So this exponential minus j2 pi over n can be replaced by simply Wn, and this is the DFT equation for n number of points. Now let's assume this is our x of n whose length is equal to 8 samples. So the value of n is equal to 8 and the index values are from 0 to 7. So we can write the limits of summation in the DFT analysis equation as small n is equal to 0 to n minus 1 for x of n. Now in order to apply radix-2 FFT algorithm on the given time domain signal, we must have to represent this original sequence into two sequences of equal lengths, where the first sequence contains even index samples while the second sequence contains odd index samples, and the length of both sequences are 4 samples, so the index values are 0, 1, 2, 3 in each case. Now our task is we want to represent these two sequences mathematically as we did for an original sequence. So let's think about it, how we can represent an even indexed samples and odd index samples mathematically. So this is how we can represent these two sequences mathematically. Now let's observe the limits of summation. For an original sequence, the limits of summation were from 0 to n minus 1. But after representing n point sequence into two sequences where each sequence will contain n by 2 samples, the limits of both summation will be from 0 to n by 2 minus 1. So if the value of capital N is equal to 8, then 8 divided by 2 will be 4 and 4 minus 1 will be 3. So the limits of summation in both cases will be from 0 to 3, as you can also see in the diagram. Now let's come to the function x of 2n. On substituting the values of n from 0 to 3, you will get x of 0, x of 2, x of 4 and x of 6. So this is how we represent even index samples. Similarly, on substituting small n is equal to 0 to 3 in this function, you will get x of 1, x of 3, x of 5 and x of 7. Let's take an example of n is equal to 2 in both functions. When we will put n is equal to 2, it means we are considering this index value. On substituting n is equal to 2 in this function, we will get x of 4. Similarly, when we will put n is equal to 2 in this function, then 2 multiplied by 2, 4, 4 plus 1, 5. So on substituting 2 index in this odd function, we will get x of 5. Now we will apply these observations in the DFT analysis equation. So this is how we can divide an original x of n which was written in the DFT analysis equation into two sequences, where the length of each sequence is n by 2 samples, and we have also changed the n variable. Here n is replaced by 2n in order to get the even index sample values. Similarly, here n is replaced by 2n plus 1 in order to get the odd index sample values. Now here you can see this complex exponential function contains two terms which can be written separately like this one, and this exponential minus j2 pi k over n is basically a constant for a given k, so it can be taken out of the summation and we can write this factor outside the summation like this one. And we already know by definition Wn is equal to exponential minus j2 pi over n. So we will replace exponential minus j2 pi over n in this equation by a Wn notation. So this exponential minus j2 pi over n, which is written with black color, can be replaced by Wn, and this 2kn will become the superscript of this Wn notation. Similarly, this exponential minus j2 pi over n can be written as Wn, and this k will become the superscript of this wn factor. Similarly, this exponential minus j2 pi over n can be written as wn, and this 2kn will become the superscript of the wn factor. So this is the DFT equation which we have obtained so far. Now let's focus on the subscript value of the w factor. The subscript of the w factor shows the length of DFT, or in other words, it tells the number of rows and number of columns in the W matrix. And as we already know, the length of these two sequences are n by 2 samples, and we have to multiply these sequences with a W matrix. So we cannot multiply them directly because it has n rows and n columns and it contains n by 2 samples. So what we want to do, we want to get n by 2 in the subscript of this W factor, not the capital N. Or in other words, to justify this thing, since we have to take n by 2 point DFT, so we must have to get n by 2 in the subscript of the W factor, because the subscript value of the W factor shows the length of DFT. Now, how we can get n by 2 in the subscript of the W factor, let's see here. By definition, we know Wn is equal to exponential minus j2 pi over n. Now, just imagine what will be the value of Wn by 2 factor. So you can simply divide n by 2, nothing else. If Wn is equal to this thing, so definitely Wn by 2 will be equal to this value. Now, let's come to this factor, which is square of the Wn factor, in order to just check what will be the final result. So if we will take square of the Wn factor, it means we are taking a square of this factor, because Wn is equal to this thing. And these two powers could be multiplied, and this 2 can also be written in the denominator like this one. So what is the final observation? Mathematically, square of the Wn factor is exactly equal to a W factor having n by 2 in its subscript. There is no difference between them. Wn square and Wn by 2 both are equal. So we can apply this observation in the DFT equation. This Wn square will become Wn by 2, where n by 2 is in the subscript of W factor. Similarly, this Wn square will be replaced by Wn by 2, and this Wnk will remain as it is. Now, if you observe these two expressions carefully, you will find these expressions are representing the DFT equations. But for how many points? Since the length of signal is n by 2 samples and the subscript value of the W factor is also n by 2, so this is the DFT equation for n by 2 points. So this is the first n by 2 point DFT. Similarly, this equation is also representing n by 2 point DFT equation. So this is the second n by 2 point DFT. And this Wnk factor is simply a multiplication factor which is introduced in the second n by 2 point DFT. And we will discuss this factor Wnk in detail in the upcoming slides. The thing to remember is that the first n by 2 point DFT outputs will appear as it is, while the second n by 2 point DFT outputs will be multiplied with some multiplication factors Wnk before addition, and we have to consider this thing during the reconstruction phase. So this is how we have divided an n point DFT into n by 2 point DFTs. And if the value of n is 8, then it means we have divided an 8 point DFT into two 4 point DFTs. The first 4 point DFT will produce 4 samples at its output. The second 4 point DFT will also produce 4 samples at its output. Now, before combining these 4 point DFT outputs, we have to multiply the second 4 point DFT outputs with W80, W81, W82 and W83 in order to get the first 4 samples of the 8 point DFT output. So in this way, we can calculate first n by 2 samples of an n-point DFT. And please remember that these two DFTs will repeat themselves after n by 2 samples because the length of signal is n by 2. And this is the reason why we have substituted k is equal to 0, 1, 2, 3 in the case of capital N is equal to 8. Now, for the remaining n by 2 samples of an n-point DFT, we will run equation A for k plus n by 2 in order to check what will happen if we will run this equation for k plus n by 2. So let's substitute k plus n by 2 instead of k in equation A, and this will be the resultant equation after making this substitution. Now let's consider this factor which is present in both the n by 2 point DFT equations and try to simplify it. So this factor is here. When we will open the bracket, we will get these two terms, and we can simplify the second term very easily if we will apply the definition of the W factor. So this Wn by 2 can be written mathematically as exponential minus j 2 pi divided by n by 2. And on simplifying these numbers, we will get exponential minus j 2 pi n, which will always be equal to 1 because by definition it is equal to cos 2 pi n minus j sine 2 pi n. And for any integer value of n, the result of exponential minus j 2 pi n will be equal to 1. Now we can simply multiply Wn by 2 kn with 1, and the final result will be equal to Wn by 2 kn. So what is the final observation? Wn by 2 k plus n by 2 into n is equal to Wn by 2 kn. So we can replace these factors by Wn by 2 kn in both the n by 2 point DFT equations. Now if we will compare equation A with equation B, we'll simply find this is the first n by 2 point DFT and this is the second n by 2 point DFT. The only difference in equation A and B is now we are multiplying the second n by 2 point DFT outputs with this factor. Now in order to make things simpler, let's assume the value of capital N is equal to 8, which is the case of 8 point FFT or 8 point DFT. So in this case, the value of small n will be from 0 to 3 as we discussed earlier, and the value of small k will also be from 0 to 3. So when we will put capital N is equal to 8 and k is equal to 0, 1, 2, 3, then we will get these factors as W84, W85, W86 and W87. While in equation A we have used W80, 1, 2, 3. So by using equation A, we can calculate the first 4 samples of the 8 point DFT output, and by using equation B, we can calculate the remaining 4 samples of the 8 point DFT output. Now let's discuss an alternate way to write equation B where we can simplify this Wnk plus n by 2 factor. Basically, this factor is a product of two terms. Now let's observe the second term. We can write this Wn as exponential minus j 2 pi over n. And on simplifying these numbers, we will get exponential minus j pi here, which will be equal to minus 1 because by definition it is equal to cos pi minus j sine pi. So on multiplying Wnk with minus 1, we will get minus times Wnk. So this is the symmetry property of the DFT output which we have already discussed in lecture 11. So we can replace Wnk plus n by 2 by minus Wnk. So this equation C can also be used for the calculation of the last n by 2 samples of the n point DFT output. Essentially equation B and equation C are very same. You can use either one of them. Now let's summarize the discussion. Equation A can be used for the calculation of first n by 2 samples of an n point DFT output because the value of k can go from 0 to n by 2 minus 1. And during this calculation, first n by 2 point DFT outputs will appear as it is, while the second n by 2 point DFT outputs will be multiplied with WNK total factors before addition. Similarly, equation C can be used for the calculation of the remaining n by 2 samples of the n point DFT output, and during this calculation, first n by 2 point DFT outputs will appear as it is, while the second n by 2 point DFT outputs will be multiplied with the total factors, which are nothing but simply the negative times of the total factors used in equation A. So if the value of capital N is equal to 8, then it means we have to reconstruct the 4-point DFT outputs. But before combining these 4-point DFT outputs, we have to introduce or multiply the total factors with the second 4-point DFT output. So in this case, for equation A, we will have the total factors values will be W80, W81, W82 and W83 because K is equal to 0 to n by 2 minus 1. So 8 divided by 2 is 4, 4 minus 1 is 3. Similarly, in equation C, we will have the total factors W84, W85, W86 and W87. But these total factors W84, 5, 6, 7 will be the negative times of W80, 1, 2, 3 respectively. Now, we can write these equations A and C in a more compact form if we will call the first n by 2 point DFT as A of k and the second n by 2 point DFT as B of k. So equation A will become equation 1. Similarly, equation C can be written in the form of equation 2. Now, this is the overall summary of the radix-2 FFT algorithm. We can divide or split an n-point sequence into two sequences of equal lengths where each sequence contains n by 2 samples. Now we will take n by 2 point DFT on both sequences, and on taking n by 2 point DFT we will observe n by 2 samples as an output. Now with the help of these n by 2 point DFT outputs, we are required to reconstruct or we are required to develop the n point DFT output. For that purpose, we have to add these n by 2 point DFT outputs, but we are not allowed to add these n by 2 point DFT outputs directly. First n by 2 point DFT outputs will appear as it is, while the second n by 2 point DFT outputs will be multiplied with WNK, which are so-called total factors. Now we can apply the same idea of decimation and reconstruction for the later stages. Each of these n by 2 point DFTs can be calculated with the help of two n by 4 point DFTs, where the first n by 4 point DFT will appear as it is, while the second n by 4 point DFT outputs will be multiplied with Wn by 2k total factors. And same is the case for this n by 2 point DFT. Now, why we have used Wn by 2k total factor here? Because when we were combining n by 2 point DFTs, we have used WNK total factor, which we have observed during the derivation. So if you will perform the derivation and decomposing n by 2 point DFTs in the form of n by 4 point DFTs, then you will find Wn by 2k total factor. Now, each of these n by 4 point DFTs can be calculated with the help of two n by 8 point DFTs, where the first n by 8 point DFT will appear as it is, while the second n by 8 point DFT will be multiplied with Wn by 4k total factors. And you can follow the same pattern for the remaining three n by 4 point DFTs as well. So if the value of n is equal to 8, then 8 divided by 8 will be 1. So this is the case where we are calculating 1 point DFTs. So we cannot proceed further. We can perform radix-2 FFT for 8 points into 3 stages. We cannot split one sample into half-half sample. And The multiplication factors which are used in this process are Wn(k), Wn by 2k, Wn by 4k, which are collectively called as toroidal factors of the radix to FFT algorithm. Now let's come